Hey everyone, I'm Suha. I'm an undergrad CS major at Georgia Tech and a security engineering intern at Trail of Bits. During my internship, I worked on Privacy Raven, a comprehensive privacy testing suite for deep learning, optimized for usability, efficiency, and flexibility. Essentially, I built a Python library that allows users to simulate privacy attacks on any deep learning system. So your first question might be, what do privacy attacks on deep learning even look like? Imagine that you're tasked with securing this medical diagnosis system here on the right. As you can see in this diagram, users determine if a patient has a brain bleed by sending in an image and receiving a yes or a no answer. The users are given as little access to the deep learning model as possible. Therefore, one may be inclined to believe that there's not much an adversary can actually learn about this system. Let's see what an adversary simulated by Privacy Raven is capable of, even when strongly restricted. So the adversary first launched a model extraction attack to create a knockoff, stealing the intellectual property of the model. They were also able to reconstruct images from and even re-identify patients inside of the training dataset through what is known as a model inversion and a membership inference attack, respectively. They were able to do this when only receiving a simple yes or a no from the system, and they used less than 15 lines of Python for each attack. I'll cover these classes of attacks one by one later, but most importantly, you just found some major confidentiality violations within the system. Presently, the attacks provided by Privacy Raven use the strongest possible threat model. In other words, the adversary only receives labels from an API that queries the deep learning model. This is known as a label-only black box threat model. A weaker threat model would be white box access, where the adversary can access information about the target, like model parameters or loss gradients. Some black box attacks also assume that the adversary receives full confidence predictions. But by operating in the most restrictive setting for an adversary, Privacy Raven can analyze the worst case scenarios. This tool is designed to be used by a wide range of people. This could potentially include a security engineer analyzing the susceptibility of their bot detection software to privacy attacks, a machine learning researcher evaluating different types of privacy-preserving machine learning techniques, or developing novel privacy metrics and attacks, or a privacy researcher building an auditing tool for data provenance by repurposing membership inference attacks. First, let's look at model extraction attacks. Model extraction is what enabled the simulated adversary to create a knockoff version of the target. This is formally known as extracting a substitute model. The motivations behind model extraction tend to fall into two categories. Adversaries that launch attacks optimizing for high accuracy are usually financially motivated. Having a substitute model means that they can avoid paying for the target in the future, and they can profit off of their own version. Meanwhile, adversaries optimizing for high fidelity want to learn more about the target. The substitute model extracted using this attack allows the adversary to then launch other classes of attacks, such as adversarial patches or model inversion. The different methods of model extraction found in the literature sometimes take wildly disparate approaches, which leads to other tools and implementations treating each extraction attack distinctly. Instead, while building Privacy Raven, I partitioned model extraction into multiple phases that encompass most attacks found in the literature, notably excluding cryptanalytic extraction approaches. The diagram shown here is a very high-level overview. The repository contains a much more fine-grained analysis if you're interested. So first, some synthetic data is generated. Then, a preliminary substitute model is trained upon that dataset. Next, the model is optionally retrained using a subset sampling strategy for performance optimization. This modular approach means that users can quickly switch between different synthesizers, sampling strategies, and other features without being limited to configurations that have already been tested and presented. For example, a user can easily combine a synthesizer found in one paper on extraction attacks with a subset sampling strategy found in yet another. Here is how you would launch a model extraction attack in Privacy Raven in less than 15 lines of code. So in the first part of this example, a query function is created for a PyTorch Lightning model included within the library. This part will vary depending on the structure of the system in question. The victim model here is a standard fully connected neural net trained on MNIST. Next, the eMNIST, or the extended MNIST dataset, is obtained in order to see the attack. The bulk of the attacks contained within this final portion. Notice that since the only requirement from the model is a query function, Privacy Raven can be used to attack almost any deep learning system, no matter what it was originally written in and how it is currently being distributed. Here, the knockoff synthesizer is being used to train the ImageNet transfer learning classifier. The other classes of attacks can be launched in a very similar fashion. The interface shown here is known as the core attack interface. Privacy Raven also provides wrappers around specific attack configurations found in the literature, and a run all attacks feature. This means that users can choose to automate much of the internal mechanics or directly control it when necessary, based upon their use case and familiarity within the domain in question. So the output of this attack would take at least 10 minutes to generate. Instead of showing you the whole output, I'll explain what's contained inside of it. First, Privacy Raven would show you statistics about the target model. Then it would provide details about the synthetic dataset and the resulting substitute model, including training progress and efficiency metrics. Finally, it would display measurements for the accuracy and fidelity of the substitute model, and in turn, the model extraction attack. Now, let's learn about our second class of attacks, membership inference. Going back to the example of the medical diagnosis system, the creation of that software relied upon many patients being willing to trust the developers with their private medical data. If a patient's participation and in conjunction with that, their image and diagnosis could be recovered, it would, first of all, violate HIPAA, and then it would diminish the trustworthiness of the whole enterprise. Membership inference attacks, at their core, are re-identification attacks that achieve precisely that. As with model extraction, I adopted a phase-based approach, of which a high-level version is displayed on the right. Before I delve into the framework, I'd like to note that Privacy Raven is one of the first implementations of these attacks under the defined threat model, which is specified in the paper shown on the left. The bulk of the attacks performed by what is known as an attack network, a binary classifier that determines whether or not a data point is inside of the target training dataset. So the dataset for that model comes from combining robustness calculations serving as a proxy for confidence with the outputs of a substitute model generated from a model extraction attack. It's important to note that, unlike other tools, Privacy Raven integrates the extraction API, making it much easier to optimize the first phase to achieve better performing attacks and ultimately stronger privacy guarantees. On to our final attack, model inversion. This class of attacks is a much more nebulous area of work, which means that we couldn't adopt an all-encompassing phase-based approach. What a model inversion attack does is that it looks for data that the target has memorized. In the medical diagnosis system, this was a reconstruction of the images the target was trained upon. The image on the right here shows the results of a model inversion attack on a facial recognition system. As with membership inference, the Inversion API integrates the extraction API, so users can benefit from customizable and optimizable extraction once again. In the defined setting, these attacks actually function by training a neural net to act as the inverse of the original model. Technical details related to that are beyond scope, but are covered further in the repository and a couple of other places. Before I finish this talk, I want to mention some Privacy Raven features that are still in incubation. By the time that you're viewing this talk, some of these may have already been released. So in addition to adding more methods for the previous classes of attacks, we're working on a new interface for metrics visualization that prioritizes clarity, as well as automated hyperparameter optimization for more coverage and stronger privacy guarantees. We're also working on the verification of differential privacy mechanisms and privacy metric calculations. More classes of attacks, including ones that specifically target federated learning and generative models, as well as property inference and side channel attacks, will be incorporated into Privacy Raven in the future. Finally, we're planning on adding models that have already implemented privacy-preserving machine learning techniques. The hope is that in 5 years, machine learning assurance tools like Privacy Raven will be as commonly used as tools like libfuzzer are for other software. Ideally, the majority of publicly deployed ML systems will implement privacy-preserving machine learning, and there will be much stronger defenses and mitigations for the multitude of failure modes in machine learning. Privacy Raven can be found on the Trail of Bits GitHub. It's an ongoing project, so we invite you to contribute where you can. For more information, feel free to contact me or my mentor Jim at these emails. Thank you all for your time.